Okay, this is part 2 of the Unit 3 information. We're going to start looking at types of reactions, and I've loved this meme. So in your first year chemistry class, typically you're going to learn synthesis, decomposition, single displacement, sometimes called single replacement, double displacement or replacement, and combustion. In AP chemistry, though, we can kind of regroup these into 3 other categories, and really all of those 5 original designations do organize well into the following: precipitation, acid base, and oxidation reduction. So this PowerPoint is going to focus only on precipitation and acid base reactions. Okay, for precipitation reactions, it really is what it sounds like. If you've heard the term precipitation, you know that's when we end up with a precipitate as a product, which is a solid. Really, the other details that go along with that is that the solid is formed from the mixing of aqueous solutions. And so they're dissolved ions that, when they come in contact with each other, do form this solid. This is a double replacement reaction, so you probably learned this generic form in your first year class. And to know what the identity of the solid is going to be, we're just going to have to know a very few solubility rules. So sodium ions, potassium ions, ammonium ions, and nitrate ions, if any of those ions are part of a ionic compound, which we call a salt, those are always going to be soluble in water. Okay, so here are the abbreviations of those ion formulas if you just need a refresher. So if we see any of these ions, they can't be the solid. All right, so that's just a reminder. It would be the, if you know this is a precipitation reaction, it would be the other product you would assume would be the solid. So along with precipitation, it's good to do some examples, and we really need to go a little bit deeper than just writing double replacement reactions. In this example, notice solutions of potassium iodide and lead 2 nitrate are combined, and you're told the identity of the precipitate, lead 2 iodide. And then the other product would be potassium nitrate. So knowing all of those formulas, that is a double replacement reaction. And so if you're asked how would you know that lead 2 iodide is the precipitate, we can just look and see, well, it can't be a potassium salt and it can't be a nitrate salt. So really just having one of those ions in an ionic compound confirms that this has to be dissolved. But in this case, we actually have 2 ions that are both part of our rules. So if we go ahead and write this reaction, notice we have Ki, PbNO3, and then we have 2 nitrates, since nitrate has an overall -1 charge to balance out with the +2 of lead. Here is our product that is our precipitate, and then here's our dissolved AQ, meaning dissolved potassium nitrate solution. And again, we always need to make sure our reactions are balanced. Now, this is an example of a molecular equation. And if you look at these particulate diagrams, which we're really going to look at a lot of these, when we say something is a solution, the word solution, or we see the symbol AQ, what you really need to start thinking of, that means it's not bonded Ki, it's separate ions in the solution. Same thing with the lead 2 nitrate. Now the nitrate is a polyatomic ion. That is a bonded polyatomic ion, as you can see as it's labeled here. But the lead ion is separate from that, okay? So what we're saying is the molecular equation that we've always written, like in the first year class, tells us what's going on, but it's really not the best picture of what's actually occurring in the solution, because notice the 2 reactants aren't bonded, and then if we go over to the product, we can see that this very organized structure must be our solid, PbI2, and then notice this other product, potassium nitrate, is a solution. It is separate ions as well. So looking at this again, this is just a reminder, why are these split up? Because remember, soluble ionic compounds form very strong ion dipole attractions with water. Now, water is not included here because it would be really complicated, be too much to look at. But when you see these split apart ions, that tells you that that is a solution. So a better way to write this is called a complete ionic equation. So the complete ionic equation shows you what everything, if we could see it in the solution, really what it would look like. And again, remember, if we had a coefficient, remember there's a 2 in front of Ki, we have to distribute that, all right? And for Pb, and remember an NO3 was in parentheses with a 2, we have to describe, we can't leave those parentheses there with the 2 subscript. We've got to say, hey, that's 2 nitrate ions that were with the lead 2 ion, and now they're all separated. So we have all these separated ions, which is described here. The middle picture, they've just kind of put all that together in the solution. But what would these individual products look like? And this one is our solid, and then our ions are this picture right here, those separated ions. Notice this is all balanced, okay? Now, one other thing I wanted to note is if we had a different kind of reaction, obviously it wouldn't be a precipitation reaction if it's producing a liquid or gas rather than a solid, but the same pattern would hold true. Liquids and gases, we would also not split into ions, just like we wouldn't split up a solid. So in other words, the only types of things you would split into ions or a substance that is, you were told is the word solution or has that symbol AQ. Okay, well, if we take a really close look, at this complete ionic equation, we can notice that the K plus ion is exactly the same on both sides of the reaction, along with this nitrate. And notice, you can see those have even been marked out. So what does that mean? Why have I done that? Well, when we see substances that appear exactly the same, there's no difference in them, from the reactants to the products, that means nothing's happening to them. They're not reacting or not changing. And the definition of these, when you see something like this, these ions, they're called spectator ions. You might have heard that before. I really like that term spectator ion because I like to watch sporting events or plays, musical things. And, I'm in the audience. I'm just watching. I'm a spectator. I'm really not a part of what's going on. Just like these ions that are crossed out. They're spectators because they're just in the solution with the other ions that are actually part of the reaction. And so in AP Chemistry, you're going to be asked to simplify and come up with what we call a net ionic equation. And that really is the best representation of the reaction because it removes the spectator ions so that all that's left are the ions that are reacting to form something new. Okay? The spectator ions haven't formed anything new, which we know the definition of a chemical change is we end up with a new substance. Well, in this case, our precipitate is our new substance. And I kind of already said this, but then you will be asked to write net ionic equations or reactions in AP Chemistry. And again, it's because these are the only ions in the solution that are actually reacting and forming something new. Now, I would highly recommend, even though you may not be asked to write a molecular equation or a complete ionic, that's a good way to get used to being able to develop a net ionic equation, especially if you've never practiced this skill before. I would highly recommend you start with that double replacement. Think of all those states, write them out, then know what substances are aqueous that you can split into ions, and then you'll be able to see the spectators to cross out and then end up with your true reaction, the net ionic. Okay, we'll go on to the second type of reactions for this PowerPoint, and these are acid-base reactions, and these are also going to be another example of double displacement. And in your first year of pre-AP chemistry or honors chemistry, you might have called this a neutralization reaction. That's a really good example. A lot of acids and bases, we have an acid plus a base yields a salt and water, okay? So, but before we really can talk about these specific reactions, we really need to specifically define an acid or a base. So take a minute and think, well, how do you define this? Because this would have been covered at the end of the first year class, and this is something you probably didn't get to since we got out of school so early and you were at home. So think about it. Do you know what an acid and a base is? There are several definitions of acids and bases, but the one we need to focus on is called the Bronsted-Lowry definition, okay? And an acid can be any substance. I mean, we think about acids as substances that start with a hydrogen, like that, but a broader definition is an acid is any substance that can give away a proton. And when we say a proton, really that is an H+, okay? Because H+ only had hydrogen atom only had one proton and one electron. If it became an ion, it lost that one electron. All that's left is that one proton. Now, a base is the opposite. It is a substance that can, take in or accept that proton. So when you see acids, they will be classified as strong or weak. And you really do need to know the 6 strong acids, and we'll get to that in just a second. But what differentiates strong and weak acids is what they do in a solution. A strong acid is what we call a strong electrolyte. And if you think about what we said about soluble ionic compounds, they completely are separate ions in a solution. Strong acids are the same thing. There are ions in the solution, so we write them as such. Okay? Now, strong acids will have this AQ symbol, and again, we're going to completely split those up into their ions because they're strong and completely break up into ions. Now, weak acids are different, though. They also will have this AQ symbol. However, only a very small portion of the acid would actually release H+. So this is where you have to really be careful. When we have a weak acid in a reaction, we don't split them up. We leave them as their entire molecule or formula. So that would be in the complete ionic equation or even in the net ionic equation. These are weak electrolytes. They form very few ions in the solution, therefore aren't good conductors. So how are we supposed to know which one's which? Occasionally you might be told, hey, this is a weak acid, especially if it's an acid you've never heard of in a problem, but you are expected to know the 6 that are strong. So if we know the 6 that are strong, everything else will be weak. So you see hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric acid, and perchloric. All other acids are considered to be weak. Same thing with strong bases. It works exactly the same way. Strong bases are strong electrolytes. Again, they're going to have this AQ symbol. If we know the base falls into this strong category, they will totally form ions in the solution, and they will be separate ions in the net ionic equation, the complete ionic equation, because they are strong electrolytes, completely forming ions. Weak bases also will have the symbol AQ. However, the term weak for bases means the same thing as it did for acids. Very few of their molecules can take in H+. So we need to write their entire formula in our complete ionic equation and our net ionic equation. Some very common examples of strong bases are sodium hydroxide, lithium hydroxide, and potassium hydroxide. And then occasionally we will see a couple of the group 2 hydroxides. This is the most common group. So if I see any of these in a reaction, I'm going to split those into separate ions because they're extremely soluble, meaning they split into ions. Now, all other bases are weak. So we don't have to remember a lot of strong bases just like with the strong acids, but we do need to know the bases that are strong. Ammonia is the classic example of a weak base. So when I see ammonia in a reaction, since I know it is weak, I'm not going to try to split that apart into ions, and we'll see that, okay? We'll always write the formula. Even though it says AQ, we know it's a weak base and has to stay as its whole molecule. Now, there is a concept called a conjugate acid-base pair, and this is something you could be asked to identify in an acid-base reaction. And so let's just look at these definitions first. Any acid that gives away its H+ becomes a base. And conjugate just means it came from. So if an acid is going to change and be a base. So if we notice here, this is nitrous acid. It's going to give away its H+. Now it remains as just the nitrite ion. That's a base. Notice bases are absorbing H+, and they become the opposite, a conjugate acid. So in this case, water is acting as a base, and we can tell it's acting as a base because if we go from its reactant form as H2O, now it has this extra H+ that's been added. Notice it becomes a hydronium ion with an overall positive charge because it added that. So make sure your charge is balanced on both sides of your equation. So water was a base, and now it's acting as a conjugate acid. So notice forward, I have an acid and a base as reactants, and on the product side I also have an acid and a base. We just call them conjugates because they came from something else. Both sides of the reaction have an acid and a base. Just remember, an acid becomes a base becomes an acid. All you need to look for to know which is which of the reactants lost an H+. Let's look at another example of a conjugate acid-base pair. Here is HCl. Here is that ammonia we said was a weak base. So remember, what kind of acid was this? Oh, we remember it was a strong acid, and ammonia is a weak base. That's just a reminder. It's not really, you're not asked that information here, but if we could tell, if you're not sure which one of these is a base, because a lot of the bases we've seen have hydroxide in them, and ammonia does not. So I just need to look at the hydrogens. As I look at the products, I see that HCl lost its H+ to become chloride, and ammonia gained that H+ to become the ammonium ion. So that's what tells me which is the acid and which is the base. And notice on this example at the bottom, they just left off the word conjugate. They say conjugate pair. If you're asked to label a pair, notice that you need to connect the two that go together. Okay, so HCl is an acid, Cl- is its conjugate base. Ammonia is a base, ammonium ion is its conjugate acid. And then let's just do some examples like we did in the precipitation portion. If we have a strong acid and we're asked to write a molecular equation, remember this is just like double replacement, or some of you call it displacement, same thing, okay? We, hydrogen, and the hydrogen ion is being lost. And it's like, I call this, when we teach this in the first year class, like switching dancing partners. So notice when the H+ is lost by the acid, it bonds with the hydroxide from the base, and that's where this water comes from. And notice this water is going to be a liquid, all right? And then we have the salt. So an acid plus a base makes a salt and water. The salt we have here is the traditional salt we think of, sodium chloride. And we would need to know that, hey, that's soluble because it contains this sodium ion. Now, remember, this is a strong acid example, so if I'm asked to write a complete ionic equation, I've got to split that acid into ions. We know sodium hydroxide is in the strong base category, so both of those solutions are split apart. Now, do I split up the salt? Yes, because I know it's soluble. If it was an insoluble, if it wasn't in our solubility rules, then maybe it would be a precipitate with the water. But what are our spectator ions? Well, I'm looking for things that are exactly the same on both sides of the reaction. So I see the sodium is exactly the same, the chloride. Notice I can cross those out, and that's how I got that answer. So what is left? And that would be my net ionic equation. So I've rewritten this. And our net ionic equation, once we remove the spectators, is just that H+ ion is going to react to the hydroxide ion. Now they both have AQ states, and now they form, can remove that, they form water. Okay, now we'll do a weak acid example in an acid-base reaction. So you might be told this is a weak acid. If not, just knowing the 6 strong acids tells us that this is not on that list. So acetic acid, you might recognize that, is a weak acid. So notice it does say AQ. This is just the double replacement molecular equation. So we have our acid, our strong base, sodium hydroxide. We are making a salt. Notice the salt will be soluble since it contains the sodium ion, and then water, which is our pure liquid. So even though this has an AQ, when I do my complete ionic equation, I cannot break this up into ions. That's the key, and you just have to make a point to remember that. It's super important. The strong base still breaks up just like we saw in the last example. And if my salt is soluble, it also breaks up into ions, and then I have my pure liquid water. Notice in this example that there is only one spectator ion, which is our sodium ion. It is the only ion that is exactly the same on both sides of the reaction. I can't do anything to the acetate ion because it is part of this acid formula. Notice these two substances do not look the same. I cannot mark out anything else. So one spectator ion in this weak acid example. So there's my complete ionic equation again. So what's our net ionic equation? Well, if I only remove that one spectator ion, I have my acetic acid, I have my hydroxide ion. The acetate ion is a product along with water. So the weak acid example has a little bit more to the net ionic than we saw with the strong acid, strong base example. Make sure also that everything stays balanced, including charges. Notice this whole side of the reaction is -1 overall because acetic acid has no charge, and the acetate ion is -1, making this whole side water has no charge. So charges and atoms must be balanced. So here's just a summary, okay, just to help you, hopefully, be very successful with writing net ionic equations. It's a good idea to write that double replacement or balanced molecular equation. Dissociate strong electrolytes. Remember that stuff, that's a soluble ionic compound, strong acids and strong bases only. Weak acids and bases, we're going to leave their whole molecule. We're going to cross out anything that remains unchanged. Those are our spectator ions, and then what's left should be our net ionic. Now, as you saw at the beginning of the PowerPoint, the AP exam likes to give you pictures of reactions. And so I just wanted to kind of go over this. So you really need to look at, when you look at pictures like this, it's a good idea to always count, identify, which picture represents which part of the reaction, and count them. So if you see CH4, you can tell there's 1, 2, 3 of those. Just going to write that above. And for oxygen, see, to react all these methane, CH4, with oxygen, notice they're in a 1-to-2 relationship. And I have 4 oxygens. So you can see that if it's a 1-to-2 relationship, both of these can't completely react. All right? Before we get into a little bit more detail of that, go ahead and just identify, like carbon dioxide, we can tell that that's carbon dioxide, this one is, so we've got 2 of these. And then we have 2 waters that are produced from this reaction. That's the balanced example. But here you can see there's a water here, a water, and a water. So 3 waters. Now, the question says, is there a limiting, right, identify the limiting and excess reactant, because there is one of each here. The way I like to do this, I know for every 1 methane, I just mark out stuff. For every 1 methane, it's going to react with 2 of these oxygens, okay? If I have another methane, it's going to react with these 2 oxygens. Notice I have that remaining. So if something of the reactant is left over, that's our excess reactant. So we can see our excess reactant already is methane. There's no oxygen remaining, so it had to be limiting. Now, you can see the product makes sense. See, for every 1 methane that I've used, I should make 1 carbon dioxide. So if I've used 2 methanes, I did make 2 carbon dioxides. And for every 1 methane that I use, I should end up with 2 water molecules. So if I use 2 methanes, 1 methane's going to make 2 water molecules. The other methane is going to make 2 more. And you can see there's that excess reactant that we were asked about. So you would have to specifically explain those details. Now here's a drawing, and because you can not just interpret drawings, that you might have to actually draw them yourself. So notice you have bromine as a liquid going to bromine as a gas. So you need to ask yourself, what would bromine look like? Okay, what would bromine look like? How would I draw that? So we're just going to draw, as you saw in the last example, we're just drawing circles, a connected circle, and those should be connected. That's what a diatomic molecule looks like. So it said to draw 4 of those. So if I draw those 4, what do I need to do to make it look like a liquid? So you got to look at all these details. Should I have drawn one that's high in the box like that? Is that what a liquid would look like? Or would a liquid be more organized? So you have to think about those details. And then a gas. So if you could try this, that would be really helpful. And also look at the next one. Now we have bromine as a gas, and this time we have a 2 coefficient, so it's 2 bromine gas atoms. So you really need to think about, are these examples the same, or are these really 2 different things that are occurring? So hopefully, if you took the time to try this, the liquid molecules should be kind of clustered at the bottom, not as organized to make them look like a solid, but they will have their LDFs holding them together. And as this is heated, it will form, the liquid will become less organized and spread out in that container. So if I take whatever my drawing was here, it would be the same at the beginning for this next process. And then notice all the atoms, make sure I have 8 total, but those are just going to be spread out as gaseous atoms. So if you look at this, what process is happening in each box? Well, the first one, I did say LDF, there's a physical change, but the second one is a chemical change.